Okay, guys, let's go ahead and get started. So today we're going to be talking about predicates and quantifiers. So predicates and quantifiers. Okay. So consider the statement. So let p of x be the statement let's say x is greater than 3. Okay? So now this statement as it stands, this is not a proposition, right? Because we don't know what x is. Right? A proposition, if you recall, is a statement, is a declarative statement that is either true or false. This we don't know because we don't know the value of x, right? However, if we choose a value of x, then it becomes a proposition. So then, for example, p of 4 is the statement 4 is greater than 3. Now, this is a proposition, and we can evaluate the truth value, right? In this case, it happens to be that this is going to be true, okay? So in other words, we can say P of 4 is true. And another example, also maybe P of 2, right, is the proposition 2 is greater than 3. And this happens to be false. So we know that P of 2 is false. Okay? So this statement, before you plug in a value for x, so this is a predicate, okay? This becomes a proposition once you place in a value for x, okay? Now, if P of x denotes x greater than 3, we can think of this as a, right here, this can be thought of as a propositional function. Right? It's a function whose output is either true or false for whatever variable you put in there. Now note that there needs to be a domain of interest that's kind of implied. For example, I can't put like, I don't know, UHD is greater than 3. That wouldn't make sense, right? So there is a domain that is implied when you look at these propositions. Okay, so that's all that predicates are. They're statements for which you plug in a value and then it becomes a proposition. If you have something that's defining that predicate, like P of x in this case, you can think of that as a propositional function, okay, whose output is either true or false. Right? So now when dealing with propositional functions, we're often concerned about when is this statement always true? When does it happen to be false? Is it always false? These types of questions. And in order to answer these types of questions, we need the notion of quantifiers. So let's go ahead and define our quantifiers. Okay, so the first quantifier is the universal quantifier. Okay, and this is the quantifier. I'll explain what this symbol means in a moment. well, that's actually called the universal quantifier. If p of x is a propositional function, we have this. Okay, so this reads, for all x, p of x. So that's how that reads. For all x, p of x. And you can think of this as the conjunction operator over all possible x in the domain of p of x. So this would be like p of x1 and p of x2 and p of x3, and for all x sub I in the domain of p of x. I like to use this notation, the big N sign, so x in the domain of p of x. So this is a big and. It's the conjunction operator taken over all possible x in the domain. Okay? So oftentimes in here, you'll specify the domain. For example, we can say for all x that are natural numbers, and then we can say p of x will be the statement x greater than 0. So in the parentheses here, we have a propositional function, x greater than 0. We choose an x, and then we check it to see if it's true. And it turns out, so here, this will have x be an element of the natural numbers. X is a natural number. So for all natural numbers x greater than 0. That's how you would read that. Okay? For all natural numbers x is greater than 0. And you would evaluate this by just saying, okay, so the first natural number is 1, right? So 1 greater than 0. The second natural number is 2 greater than 0. So forth and so on. Okay? For every natural number x. Now, it just so happens that that's true, right? And that's true. And then if you plug in a 3, that's going to be a true. It's going to be true forever, which means that the conjunction operator is going to evaluate to true. Right? The conjunction between propositions is true when all of them are true and false otherwise. So that's what you can think of this as. So this is true only when p of x is true for all x in the domain. That's why it reads for all x p of x. Okay, so this statement here, right, this would be a true proposition. It has the quantifier for all, and every single natural number that you plug into this propositional function will evaluate to true. So since they're all true, this together will be true. Okay? So, okay. That's the universal quantifier. For all x, p of x, true, but only when they're all true. And the way that I remember is just think of it as a big conjunction of all the elements in the domain. And so next, we have the existential quantifier. Okay. So this symbol right here That is the existential quantifier. Okay. And you can think of this as a list of disjunctions among all x in the domain. So this is like p of x1 or p of x2 or p of x3 or dot, dot, dot. Ors for all x in the domain. Another way that I like to think of this is a big or symbol, where x is taken to be in the domain P. Okay. Now this here reads, there exists x p of x. So we know with the or the disjunction operator that as long as one of them is true, then the or is going to evaluate to true. So there exists x p of x is really saying, is there any x in the domain for which p of x is true? For example, so there exists x that is an integer. That's an epsilon right there, just to say that it is an integer. There exists an integer x such that x times 5 is equal to 0. Okay, x times 5 is equal. So is this a true statement? Well, this is true. So this propositional function will be false with x being 1 or 2 or anything like that. But when x is equal to 0, which is an integer, which is in there, this statement will be true. So since at least one element in the domain has this evaluating the true, the existential is going to be true as a proposition. Okay? So this is, I'm just going to write that down. True when at least one p of x is true for x in the domain. It's only false when it's false for every x in the domain. Okay? All right. So let's look at some examples. Actually, we're going to move on to nesting quantifiers. So nested. Actually, I almost got ahead of myself. We need to talk about DeMorgans laws for quantifiers. All right. So fairly simple. Suppose we would like to negate the universal quantifier on p of x. So we want to negate for all x p of x. Okay. Now, if you remember, the universal quantifier is like this conjunction over all x in the domain of t, right? So this is really like saying the negation of P of x1 and P of x2 and P of x3 and so forth and so on for all x in the domain of P. Now, just so I'm not going to get called out by anyone, I'm simplifying this where the number of elements in the domain, I'm just assuming that I can write them in a list. If the domain is not countable, which we don't know what that means yet, we wouldn't be able to technically write it out in a list like this, but it works just the same for our purposes. So I'm assuming that I can write out every domain element in P in this list. Now, here we have the negation of conjunctions, right? If you think back to DeMorgans Law, the negation of the conjunctions is the disjunction of the negations. So you negate that, that becomes an OR. You negate that, that becomes an OR, so forth and so on. So what this becomes by DeMorgans Law is not P of x1 or not P of x2 or not P of x3 or ... forever. Okay? And now we have a disjunction, a bunch of ORs for the negation of P of x, right? So, like, notice it's like proposition here, or proposition here, or proposition here, or proposition, proposition, proposition. So we have this OR over all x in the domain. Well, that's the same thing as the existential quantifier. So we can rewrite this as there exists x, not P of x. So if you negate the universal quantifier here, you get the existential quantifier of the negation. Okay? Now, in a similar fashion, if you negate the existential quantifier, so not there exists x P of x, well, this is like saying the negation of this disjunction here. So it's like P of x1 or P of x2 or P of x3 or ... Okay. But then the negation of ORs becomes the conjunction or the AND of the negations by DeMorgans Law. Not that, that becomes an AND, not that, that becomes an AND, not that, so forth and so on. So what we get is that this is going to be not P of x1 and not P of x2 and not P of x3 and ... off to infinity. There are however many elements are in the domain. But then we have, again, we have a proposition and another proposition and another proposition, and for all elements in the domain of P, so what this becomes is the universal quantifier. So this becomes for all x not P of x. So when you negate the existential quantifier, you get the universal quantifier of the negations. So these are the two fundamental laws for quantifiers, the DeMorgans laws for quantifiers. Okay? So these are really important to remember. If you negate the universal, you get the existential of the negation. If you negate the existential, you get the universal of the negation. Okay? So Really important to note this. And again, the same, so these are propositions, right? So if you have a quantifier that has evaluated to true, and you take the negation of that quantifier on a propositional function, then it should be false. If the original quantified proposition is false, then if you negate that, it should become true. So the same properties that hold for propositions hold for these quantifiers, because these are actual, they're propositions just like we've been dealing with. Okay. So let's look at some examples, maybe. Okay. Yeah, let's do some examples. Let's say, and that are integers. N plus 1 is greater than n. So A, B, say there exists n that is an integer such that n is equal to this. C, there exists, let's do for all. And so here are three quantifiers on predicates or propositional functions. Okay, so take a moment and think about these. So any of these false, are these true? So take a moment to think about it. Okay, so what about part A? Is part A true or is it false? For every integer n, n plus 1 is greater than n. True, right? So this statement holds for every integer. If you add 1 to an integer, you get a larger integer. Okay? So what about this one? Is this true? There exists an integer n such that n is equal to negative n. By the way, notice what I just said when reading these. There exists an integer n such that the proposition, so such that n is equal to negative 1. That's how you would read these. So this is true, right? The integer 0. 0 is an integer, and 0 is equal to negative 0. So since it's true for that 1, or at least 1, this whole existential quantifier evaluates to true. And this one, false, right? So this is false since 3 times negative 1 is not less than or equal to 4 times negative 1. Okay, so this is what's called a counterexample. So n equals to negative 1 is a counterexample to part C. So a counterexample is just a element in the domain that shows the statement to be false. That's all a counterexample is. Okay. Okay. And then this is a good one. So what is the negation here? Yeah. Of the statement for all x, let's say in real numbers, x less than 1 or negative 1, or x greater than 2. This is just a false proposition, but the problem is to express the negation of this statement. Now, I will go ahead and say that on the first exam, there will be a multiple parts A, B, and C, where each part is to express a quantifier, express the negation of a quantified statement like this. So on the first exam, there will be something like that. Okay. So how do we do this? Well, the solution. Okay. So we look at the negation of this universal quantifier. Okay. And this will be, as you recall, the negation of the universal is the existential of the negation. This is the DeMorgans Law for quantifiers. So this will become, there exists a real number x, such that it is not the case that this stuff here. Okay, but we're not done. Okay, we're not done because now we have the negation of the or. Okay, so the negation of the or, we can use DeMorgans Law again inside of here. So there exists x. There's a real number such that it is not the case that this. That or becomes an and then we negate the other proposition. All right, so we're almost done now, because now we have the negation of this, and we need to express that in its full form, right? What does this exactly mean? What does it mean for it to not be the case that x is less than negative 1? Well, if x is not strictly less than negative 1, then x is greater than or equal to negative 1. Okay? So this first part becomes x greater than or equal to negative 1. Okay? That still becomes and. So if we negate x greater than 2. So if x is not greater than 2, it is less than or equal to 2. So this is the full negated form of that statement. Now notice, for all x that are real numbers, x less than -1 or x greater, this is false, right? However, this is true. There does exist a real number that is greater than -1 and greater than or equal to -1 and less than or equal to 2. There's a few of them. 0, 1, -1, 2, every real number in between that interval, right? So this is true because that was false. If you negate a false statement, you get a true statement. Okay? Okay. All right. So I think that's it for today's lecture. Next time, we're going to look at nested quantifiers. And then next week, we're going to start on actual proof writing. Okay? So I forget when the homework is due, but I'm going to, if it's not due next weekend, I'm going to make it due next weekend. That way, I'll be able to go over proofs with you in lecture next week. Okay? All right, so that will be it for today's lecture. Everyone stay safe. And I will see y'all on Thursday.
Hey, Professor.
Yes.
I just got a little question.
Mm-hmm.
Are you gonna post last Thursday lecture on the Blackboard?
All lectures now will be posted on YouTube.
Oh, all right. Thank you.
Mm-hmm. Okay, guys, stay safe.